Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 4B of this electrostatics chapter. So today we'll learn the electric potential due to more finite charges. Also, we will learn the concept of cavity in conductors. Actually, I told about it. Like I gave you a bit of overview before two lectures, but I didn't clear the concept there because we had to learn the concept of potential as well. That's why. So we'll understand more about cavity of perfect conductors. But before starting, I promised you that I gave you a few homeworks. So those I will solve here. Okay. So this was the first question that I gave you. I have already solved, I think. So this was the question basically. In this question, what we had to do, we basically had to find out the work done due to the different paths, right? First of all, the first question I solved using the principle of conservative fields. Electric field is conservative in nature. So if I come back in the same point, the work done will be zero. I will prove it using the second solution of the second question. So here we have to find out the work done due to each path. So if I take the first path C1, what is changing here? Just a minor change here because this was X and Y, right? Previously it was in this direction, the positive Z. Now positive Z should be downward because I have to follow the right hand rule, but it doesn't matter because here Z is constant, that is Z is 0. We are only talking about XY plane. So I am moving from this point to this point. So in the first curve, one thing to note is that electric field will always follow this function. Electric field will not change. It will always follow this function, but other things will change. The path C1 will be how? It will be going from 0 to 0 to 1 0. So one thing I am observing that my x is changing, that dx is not equal to 0, but dy is simply 0 because here no change in y, right? Simply only x is changing. So dy and dz will be 0 because anyways dz is constant. So dx is not equal to 0. So I can put in this integration what will be E dot dl? dl equals to dx plus dx a cap, dx ax cap plus dy ay cap plus dz az cap. So dz is 0. dy is 0, so all those things go away. Only dx ax cap is remaining. So I will only take the ax cap of the electric field because ay dot anything else will be simply 0. Only ay dot ay will be 1. So this component will be present here. So this is what I will integrate. Okay. Now if I integrate this here, one thing I know that y is 0 throughout this whole curve. Y is what? Y is 0, right? Y is not changing. Y is 0. So I will replace this y is 0 and I will integrate x from 0 to 1. I will get the value of 0.5 microjoules. The same procedure I will follow here. Okay. Minus q, don't forget the minus q. As q is already negative, so this becomes plus. Okay. This overall becomes plus 0.5. Okay. This becomes plus. For second curve, what is happening? For second curve, here I can observe that my electric field, like this curve, right? What is changing? Is x changing? No, right? Dx is 0. Dx is not changing. Dy is changing from 0 to 1 and dz is anyway 0. So same thing I have written over here. Dx is 0. X is not changing. Dz is not changing. Z is not changing. Dy is not 0. So this time dl vector will be equals to what? Dy ay cap. Dx is 0, so that goes out of the picture. Dz is 0, so that goes out of the picture. So I have only the y component of the electric field. What is the y component? 2x ay cap. And what is x here? X is 1. In this, throughout this whole line, x is 1. So I will replace that x equals to 1 and now I will simply integrate with respect to dy. I will get 2 microjoules. Okay, this will be 2 microjoules. Same step I will follow here. Again, I will see here. Interestingly, everything is changing. X is changing and y is changing. According to what I can use this format, right? I can convert it into a single parametric equation. I hope you have studied integration from me. If you have studied, then you will not have any questions here. If you haven't, then you have questions and I will not answer. Okay, you have to go and back and study the calculus chapter. Okay, so you can convert this into a single variable t and you can write the limits of t. So t will go from 1 to 0. I have just converted according to my convenience. So then if you solve this, right, you will get back your value as minus 5 by 2 microjoules. Now if I add, what will be the total work done? Total work done, like individual path of work I have computed. What will be the total work done? Total work done will be the scalar sum of all the individual paths, individual work done. If I add all this through, what will happen? This is 0.5, this is 2.5 minus 2.5. Overall this becomes 0. Okay, hence I already, without doing anything, without even touching the notepad, I directly told you the answer will be 0 for a closed work done due to the closed path, right? Already told you. Okay, so that's the power of conservative fields. So I hope you understood this point. So I proved to you as well, the work done will be 0. Now let's solve these questions. So these particular questions where we had to compute the potentials. So here for part 2, right, what will happen? Again, I am going from A to B. If I am going from A to B, I will observe the angle. What is the angle? My dl vector is in this direction, right? Dl vector is in this direction, and my electric field is in this direction. Okay, so this will be theta. So I will actually apply force on the left hand side, right? So I have to find out the angle between the force, right? So force will be applied here. So this is not the theta actually. The theta will be on the left hand side. So here what can I observe? The theta is always less than 90 degrees, right? Here if I observe, theta is always less than 90 degrees. 90 is here, correct? If theta is less than 90 degrees, what can I comment on? What can I comment? I can comment that my delta V will be negative. Sorry, delta V will be positive because cos 60, cos anything less than 90 is positive, right? So my delta W work done will be positive. Hence my delta V also will be positive because it is just a division of charge, right? Division of charge, positive test charge. So I can say VB minus VA will be greater than 0. So what I can comment? I can comment VB is greater than VA. Okay, VB is greater than VA. So this is what I can comment here. Okay, so like similarly you can do for the other cases as well. So I will do it for the third case as well. For the third case, it is pretty simple, and this concept we will learn in today's lecture actually. Here what I can observe is that my force will be in the left hand side, right, and DL is already at the top. So the angle I can see is directly 90 degrees always. So if theta is always equals to 90 degrees, what is cos 90? Cos 90 is 0, right? So delta W will be 0. Hence delta V will be 0. Hence VB minus VA will be 0. Hence VB will be equals to VA. Simple. So this also is known as equipotential lines. Why are they called equipotential lines? Because the potential is same throughout the whole line, right? Potential doesn't change. The point potential here, the potential here, the potential here is same. VA minus VB is 0. This is what we learn in this lecture, in today's lecture basically. Next is this one. So like you can do for all this, right? This is just a futile exercise. So if I copy and paste, here again this will be actually always negative. Here I can observe that angle is exactly equals to 180 degrees, right? Because my DL is in this direction and my force will be in this direction in opposite to the electric field. Okay, so what will happen? Again, same case as this, right? Same case as this. Theta will be exactly equals to 180 instead of greater than 90. It will be exactly equals to 180, but all the other things will remain same, right? Delta W will be less than 0. Okay, so here theta will be exactly equals to okay 180. So yeah, that is the case. Everything else remains same. Again, if I pick the fifth one here, right, again theta is 0, so it will just follow the second case. Here my theta, if I just say, force direction will also be same as DL, so angle between them is 0, right? There is no angle between them, so theta here is 0. So we'll copy and paste this one. Theta is 0. Okay, so delta W will be greater than 0, delta V will be greater than 0, and VB will be greater than VA. Now this case, the final case is a bit interesting. Okay, can tell me what will happen in the final case. So in the final case, right, actually from here to here my DL is changing. So if I just pick a third point C, okay, so at C my direction of force is this will not change, okay, and my DL direction is also same. So for C, what I can comment, that theta C is equals to 0 degree. So if theta C is equals to 0 degree, it will follow this chronology, right? It will follow this chronology, that work done for the charge to move from A to C will be simply positive. So VC will also be positive. Hence, I can say VA minus VC will be positive. Hence, I can say VC will be greater than VA. This much I can comment. But what about this case? So here I can observe that my force direction will be on the left hand side, always opposite to the electric field. But DL has changed, right? DL is on the top. So here what I can comment is that my angle between DL and my force is 90 degrees. Correct? The angle between DL and force is 90 degrees. So what I can comment is that my theta B is not, I'm just picking notation as my will. Okay, theta B doesn't represent anything standard. Okay, and just picking that angle during the second phase of DL is 90 degrees. Okay, so this is my theta B. Correct. So now what I can comment is that here what will happen is that my delta B will be 0. Hence my, because cos 90 is 0, delta VB is 0. Hence my VB will be equals to VC. So it will not change. Ultimately, the relationship between VA and VB will be what? As VC is greater than VA and VC is equals to VB. So VB will be greater than VA. Okay. So like this you can solve. Pretty simple. Okay. You could have skipped all this, directly done that. Okay. I will recommend you directly doing it. As I am explaining it for the first time, that's why I am doing all this. In your mind, it should all click and directly you should write this expression. Okay, so that's what you should do in the examination hall if these type of questions come. So another question that I gave you as homework was this particular question. Now, where did it go? Yeah, this one, right? This one is again pretty simple question, right? You have been given electric field in cylindrical coordinates. You just have to find out the potential between points. You will just use the simple formula. What is the simple formula? It is potential equals to minus Q in integration from A to B E dot dl. Okay. Now here A and B are actually different. The points that are given are actually in Cartesian coordinate system, and the electric field is defined in cylindrical coordinate system. So what you will do? You will simply convert these points, right? You will simply convert these points. So here what you can do is you can do this your rho A is what, or what is a rho P. Rho P is what? Rho P is x square plus y square. If you remember, rho P is x square plus y square, so it will be under root 1 square plus 0 square, so it is 1 only. And what about your rho Q? Rho Q is under root 4 square plus 0 square, so it will be 4 only. Correct? So rho is changing like this, and your DL, right? It is only in a row vector, so I have to only take care of the row limits. So rho I have to only take care of the row limits. So rho A is changing from 1 to 4. Okay, so things become simpler. Like this is what you have to think in the examination hall. This is only in the aero cap direction, so I will not take care of the other directions like A phi and AZ, because my DL vector is actually, I will write here, DL vector in cylindrical coordinates is d rho aero cap plus rho d phi a phi cap plus dz az cap. But I will not take care of this. Why? Ignore. Electric field only in aero cap direction. So if I take the dot product, all this will anyways go to 0, vanish. So I don't care. I only care about this. So the solution will be much simpler. So V from P to Q will be what? Minus Q charge they have. Okay, no. So it will be simply minus E dot dl, right? Minus E dot dl. So here it will go from rho A P to Q E dot dl. So I can directly replace. It will be going from rho A, rho equals to 1 to rho equals to 4. E is this. Now just keep in mind that you have to break your integration, because from 0 to 2 the definition of electric field is something else, and from 2 to greater than 2 the electric field definition is something else. So I have to break down the integration. Okay, E dot dl. So what I will do, I'll just break down the integration. So my VPQ will be minus integration E dot dl from rho equals to 1 to 2 whole brackets plus integration rho equals to 2 to what was it, 4, right? So this type of breakage you have to do because the function definition is changing, and if you are not able to understand how am I integrating, go back and watch the calculus lecture. Okay, so because there I have taught everything from basics, I will not repeat here over again. So this will be negative, and now I will finally write the definitions, right, of electric field. So from between 0 to 2 the definition is 5 by rho, right, and a rho cap dot product is 1, so this will be d rho, plus from 2 to 4 the definition changes, that is 2.5. It is a constant thing, and this will be d rho again, correct? So this will be equals to minus ln 5 is at the outside, ln 2 by 1, right? Yeah, ln 2 by 1. So this will be ln 2 plus 2 into 2.5, so 5. This is my VPQ. I will just quickly compute what is ln 2 actually. What is ln 2? We'll quickly compute. So this will become 2 ln and plus 1 into 5. So this will become almost 8.46, and obviously don't forget the sign. So this will be minus VPQ will be minus 8.465 volts. Okay, so this will be the answer to this particular question. I hope you got the gist of the question. So first of all, you have to understand how to integrate. First of all, you have to understand what to ignore. Okay, because if you try to take all this into account, it will consume time. So you have to save time in the examination hall. So that's how I save time, right? I didn't take care of the, I didn't care about the phi, I didn't care about the z, I just care about the rho. Okay, anyways, you can observe that z is not changing here, dz is 0. So anyways, it becomes simpler. So let's now start with today's lecture 4b. So first of all, we'll again redo the conductors part, because at that point of time I didn't explain it clearly about the charge distribution, right? I will just explain it again, and I will again revise the properties of conductor, because at that point of time we didn't study the potential difference. So if I say the properties of conductor, this is the key, this is the point that you should put in your short notes, or if you want to remember the main thing about conductors, right, you should remember 3 points. First point, electric field inside a perfect conductor will be 0. Okay, first of all, you have to understand that this is a perfect conductor. This also you have to keep in mind. Now, charge inside a conductor will be 0. Why? Because electric field, as electric field is 0, as my electric field is 0, then my E dot dl will obviously be 0, because magnitude itself is 0, right? If this inside part is 0, then obviously this will be equals to 0, which is equals to my charge enclosed. So obviously my charge enclosed inside a conductor will be 0. So what will happen basically, if I by any chance forcefully keep a charge here, all the charge will go towards the boundary, towards the surface. That will what will happen at steady state. So that's how the electric field will not be generated inside the conductor. Okay, so this is what happens inside the conductor. Then next, third point, which I didn't mention previously, was the potential difference also will be constant. Why will be the potential difference constant? We know what is my potential difference. Potential difference VAB is also equals to E dot dl, if you remember, right? VAB is also equals to minus E dot dl. So again, this whole thing is 0, so potential difference also will be simply 0. That's why potential difference is 0. That means the potential at this point A and at this point B is same. Potential is same. Absolute potential VA is not 0. Potential is same between all the points of the conductor. Here, all the points have same potential, also known as equipotential. This type of concept we will learn in today's lecture basically. So main takeaway is potential is not 0. Potential is same at all points, not 0. not necessarily 0, it can be 0 as well, but the main meaning of it is same. Okay, so with cavity I will explain the conductor once more because I have explained this previously. I will just repeat it once more. Okay, so here let's say I have a conductor. Okay, S2 is a conductor. Okay, perfect conductor. Now I remove some part of S1 from S2. I remove S1 part. Okay, from inside. You remember cavity, right? Inside your teeth you have cavity. If something is removed from the volume, cavity means something removed from the volume. Okay, that is what cavity means. So if I somehow remove something, so this becomes air. Okay, and inside air charge can stay, charge will not go away. So then I place a charge, then I place a charge just hold on. Okay, sorry. Then I place a charge inside vacuum. It become vacuum, right? Or air. Now it will not move, it will stay as it is. Okay, because this is not a conductor, this is simple vacuum. So what will happen, due to this positive charge inside, like this section is still conductor, right? So whatever electrons are present, they will be attracted to this positive charge due to induction, right? Due to method of induction, I will write here, due to induction, all the electrons will get attracted to plus Q. So what will happen, whatever electrons were present in this conductor, right, they will be surrounded on this, because obviously they cannot go outside of the conductor, they will remain at the surface of the, like, inside cavity of the conductor. Okay, now due to this negative charges, what will happen is that how much will it generate? Overall it should generate Q, minus Q of charge. Why? Because due to the first property of conductor, electric field inside a conductor is 0, right? This part is still conductor, so if I take a Gaussian surface here, the electric field should be 0. So to make the electric field 0, this has to be minus Q. Okay, so I will write here, to make electric field 0, I will make here minus Q, right? So next, what will I do? Next is, again, in this surface as well, in this overall surface, what should happen actually here? So here charge needs to be conserved, right? Here I have got some minus Q amount of charge, here I have got some minus Q amount of charge, so charge needs to be conserved. So if I take a Gaussian surface here, it is telling me I have 0 charge, but actually, to be honest, some of negative charges have been placed. So as charge needs to be conserved, due to this negative charges, this has, like, through this conductor, minus Q has been generated. So plus Q will also be generated, because that will obviously make charge conserved, because inside this conductor the charge was 0, but I got minus Q charge, so I need to make the charge 0. So finally I will have charge on the outside of the conductor, that is positive charge, right? Plus Q. This plus Q comes due to charge conservation. Okay, charge conservation. Obviously initial and final charges must be same. Charge cannot be destroyed, neither created, right? Okay, so this is the case of charge conservation. So now the important point is that you don't need to do all this step process, right? What you need to keep in mind in in your head is that whenever there is a cavity, there is a conductor, you just try to solve it like this, that there is a charge inside plus q. So due to this plus q, a minus q will be generated here. Reasons I have explained. So don't think about reasons, just understand what will happen. And due to this minus q, again charge conservation will take place. Again a plus q will be generated at the surface. Okay. So overall charge is conserved and electric field outside will be radially outwards. Okay, electric field outside will be radially outwards, but inside the conductor, zero. There is no electric field, right? So how will the electric field look like? Electric field, this is air, right? This is air, so it will be here, here, here. Again, it will not be here in the conductor, but it will be outwards from the conductor. So internally, this much thing is happening, right? And due to this, electrostatic shielding is happening because inside conductor there is no electric field, so it basically shields the region from any electric field. Okay, so this is the what is written. Electric field lines do not exist inside a conductor as the field within a conductor is zero. All this is like explained here. Any charge placed inside the conductor will automatically move to the surface of the conductor, automatically spread out. Okay, so these points I think you can read. Now we'll start with our potential discussion that we were doing in the previous lecture. So today we'll do it for the finite charge distributions. So this doesn't get asked much often, but still if you have if you have to compute in generalized expression, not for a standard expression, this is how you compute. You take a small charge dq as a function of dl, ds and dv, that is as a function of small length for line charge distribution, small surface for surface charge distribution, small volume for volume charge distribution. Then you write the differential potential. How do you write the differential potential? We know the potential due to a point charge is q upon 4 pi epsilon r. So the potential due to a small charge, it is also assumed to be a point charge. It will be dq upon 4 pi epsilon r. That is dv equals to dq upon 4 pi epsilon naught r. R is the distance from dq to point P, and the other point is infinity basically. So hence the reference is taken as infinity, right? So it becomes 0. So dq I can replace here simply rho L into dl or rho s into ds or rho v into dv, and then I will just put the limits. I will just put the limits and I will solve for the expression. So we'll solve few questions, there we'll understand. So this first one, right, it is not that important. Okay, I will say not that important because the derivation is a bit difficult, so that's why I have already written it down, and this most probably will not come in your examination. Still, if you want to know the formulas, you can know the formulas, that if I have to compute the potential at point P2, how do I compute for finite line charge for non-symmetrical case? This is not non-symmetrical case, right? Not symmetrical. Okay, so for not symmetrical, this weird kind of expression comes up, so don't worry, you don't have to remember this. Maximum chances are there that this will not come in your examination. Okay, maximum chances are there. So yeah, you can skip this, but this ring charge is very, very important, so you have to understand the derivation of this. So basically whenever we talk about potential with respect to 2 points, so here the B point is at infinity. Okay, so dv is this, right? dq by r, and r is constant, like for this dq, for this dq, for this dq, for every dq r is constant. So actually the derivation becomes very, very simple. So my dv will be what? So I will integrate from what? You have to understand, dv will be from a reference, right? I am coming from reference r infinity, so this will be from infinity to v at this point P. Okay, so at infinity the potential will be simply 0, right? The potential will be simply 0 because r infinity is 0. The distance is infinity, so it will come out to be 1 by 4 pi epsilon and dq by, and what can I write? R in terms of r is actually capital R square plus h square 1 by 2. So this will come out to be vp minus v of infinity, right? V of infinity is 0 because basically this is at r infinity, and r infinity means v of infinity will be 0. Now what is the variable here? Okay, just q is the variable, right? All the this distance is always constant. If for this dq, for this dq, for this dq, everything it is just constant. So I can simply integrate. So it will come out k, no, not, yeah, 1 by 4 by epsilon is simply k q by, you can write r, or you can write this expression as well, r square plus h square, or I can write this as x square as well. Okay, if you want to write this as x square, you can write as x as well, or I will do what I will do is I will write here r naught square. Okay, for simpler, basically the distance from the foot of the perpendicular. So like reference is there. Okay, this is potential due to 2 points, but infinity the potential is 0. So I can directly say with respect to reference, the potential at point P will be k q. Like you can derive this, or you can remember this as well, this 1 by 2, right? One by 2. Okay, so this will be the potential due to a ring charge. Okay, and it is same expression as point charge, just the distance. So this is a question. Can you do this question for me? Pause the video and do this question. A circular ring with uniformly distributed positive charge lies in the xy plane. So this plane is actually xy plane, fine, with its center at origin of the coordinate system. If the electric potential at a point 0, 0, z is V, that is V, which of the following statement is correct? Okay, so basically it is asking us the change as this distance, right, perpendicular distance changes, how will my potential vary? So what I can observe, this is like a reciprocal format only, like the potential inversely varies actually with respect to the distance, perpendicular distance, but not exactly inversely, right? There is some other relation as well. So approximately I can say it varies like 1 by r naught, but not exactly, approx. Okay, but not exactly. So here what I can say is, if let's say if this r naught is very high, if this r naught is very high, I can ignore this r. So this totally is inversely proportional. So it becomes totally inversely proportional. It keeps on reducing, and at r naught equals to infinity, it will become 0. Correct? So here it is going down. But here it is telling me that as I increase my perpendicular distance, the potential also increases. Is this true? No, right? It is not possible. R naught is in the denominator. If r naught increases, potential will decrease. So this option is gone. This option also is gone. What about this option and this option? So these two options are actually pretty good. Okay, these two options are actually pretty good. So here also it is telling me potential is decreasing, and here also it is telling me potential is decreasing. So which one will I choose now? So things become a bit unclear here. Okay, so what you can do is, from these two, right, how can you differentiate? Like how can you understand that whether this will be correct or this will be correct? Both are telling that both are tending to 0, but this is actually not tending to 0. This is actually tending to minus infinity, right? But this is tending to 0, so I know that this will be option, this will be the correct answer. But even if you want to cross verify, how you can cross verify? You can actually differentiate the two functions. You can differentiate this function. If you differentiate this function, you will see that your slope will go towards 0 at infinity. But here it is telling me slope is going towards negative, infinity. Slope is always negative. So here, you can identify from slope negative. Here slope 0 at r naught infinity, at r naught infinity. So you have to identify by slope, or you can understand this is becoming an unstable potential, because at infinity it is telling me potential is minus infinity, right? It is going downwards and downwards, which is not possible. Here it is looking like it is going towards 0. Okay, stabilizing towards 0. So obviously option A will be correct here. Simple, right? And one more thing, what you can identify is this graph, although I haven't done this correctly, near 0, right, near this z equals to 0, the slope should be 0. There is no sudden change. Here there is sudden change. So from this point also I can identify, at z equals to 0, slope should be actually 0. But here at z equals to 0, the slope is like, although this graph is showing it non-zero, but it is changing suddenly. It should be actually more sharper. I should have drawn it more better, actually, my fault. Sharp change. This change is more sharper. Okay, so z equals to 0, slope is not equal to 0. Okay, so this was the solution. Like, this solution is pretty simple, but you have to identify these type of questions. These type of question can come. Determine the potential. Now let's do this next question. Determine the potential at points P, Q, R for the arrangement zone. So we have P, Q and R. Like we have these two rings, and we have to determine the potential at points P, Q and R. So I know the formula, right? What is the formula due to a ring charge? Due to a ring charge, the formula for potential is KQ upon R, basically. Simple, due to a spherical charge, same as spherical charge, right? And R is the perpendicular distance, okay? Or I can write here R perpendicular, okay, from the axis. So if I compute for the point P, right, for the first case, if I compute for the point P, this will be just be a sum of two things, two charges, due to this ring and due to this ring. So okay, sorry, not R perpendicular, sorry, this will be R only, sorry, this will be R only, which is equals to, basically, I can write here the ring radius plus the perpendicular distance from the axis of the ring. Yeah, okay. So here, actually, what is happening, due to this ring, what is the potential at point P? It is K times 2 micro divided by R square plus perpendicular distance whole square. R is 3 meter, but there is no perpendicular distance. This is on the axis itself, so it will be 0. So it will be simply 3, correct, plus K, and due to this ring, that is 1 micro, sign doesn't matter, right? Sign doesn't matter here, divided by the perpendicular distance. So this distance is 10 and this distance is 4. So overall the distance will be 10 square plus 4 square under root. So if I just compute it real quick, I will just quickly compute it. Under root, so this will become K, and micro is obviously there, I will do that, just hold on a second, plus 2 divided by, okay, I made it wrong actually, 1 minus 2 and plus 2 divided by 3. Okay, so this will actually come out to be K into, and micro is there, right? So K is 9 into 9 into 9, what do I get? 6.8. So this will come out to be 6.83 kilovolt. Actually huge voltage, because 10 raised to power 9 is there and 10 raised to power minus 6, so it will be 10 raised to power 3. So VP will be this. So you can do the same for the midpoint for VQ. What will VQ? Again, you will do the sum only. So we don't have directions here, simple sum. So at this point, what is the perpendicular what is the, like, this distance from this small charge Q, and what is the distance from this small charge Q2? So it will be, K will be common, okay, KQ into 2 micro divided by, this is 2 micro, right, and the distance will be under root 3 square plus 5 square, okay, whole under root, plus K into 1 micro divided by 4 square plus 5 square. This is also 5, right? This distance is also 5, whole under root. Okay, so this will be equals to what? I can quickly compute this, just hold on a second. 16 plus 25 under root and this is 0.156, and this should be 9 plus 25 under root into 2 plus, okay, this is 0.343 K micro, correct? So if I add this with 0.156 into 9 should give me 4.5. So this will be 4.5 kilovolt. So this actually has reduced. So between the two rings, right, the potential is actually lower. So let's calculate the potential here. What will be the potential here? So if I compute the potential at point R, so this is with respect to infinity. So I will just write at the starting itself, all potential are computed with R naught as infinity, okay, with respect to, so VR will be the same thing only here. This will be 2 micro. Now the distance here, right, it will be 10 square plus 3 square. This distance 10 square plus 3 square whole under root plus K 1 micro. Now this distance, right, this perpendicular distance is 0, only this 4, so this will be only 4. So I will compute it. So this will be 9 plus 100 whole under root plus 1 divided by 4. Okay, I did one thing wrong, I think. 9 plus 100 whole under root into 2 plus 0.25, okay, into 9. This comes out to be lowest. So this comes out to be 3.97 kilovolt, okay. This is my potential at R. Okay, so I hope you understood how do we compute the this potentials. Now another thing is there, like if instead of I ring charge, I have a disk. If I have a disk, then how will I compute the potential, right? So basically you can derive it, okay. Deriving it, the task is the homework for you. Assume multiple concentric rings, okay. So if you assume multiple concentric rings, what will happen is that each ring, right, will have its own radius. Each ring will have its own radius. So I can say 2 pi r into dr. This is the area, right? This is the dA is equals to dA, and this multiplied, like my dq will be what? Dq will be rho s into dA, which is 2 pi r dr, and then you do the limits, right? Then you do the limits of r. R is going from 0 to capital R. So if you solve this or using theta some other thing, okay, you will get this result, okay. You will get this result. It's easier for you to remember this. Remember, this is just the distance, right? This is why am I writing magnitude here? Just the perpendicular distance, okay, just the perpendicular distance I have to write. So the expression becomes very, very simple. It is rho s upon 2 epsilon into L minus R naught, and I have also explained how can you derive it, okay. So all these things I have explained. Now electric potential due to finite charge, this I think I have explained already previously, so just go through this quickly. So due to hollow or solid conducting sphere, so inside potential will be constant. What will be the potential? It will be q upon 4 pi epsilon r. Why? Because electric field inside is 0, so potential will be constant. That is whatever there is at the surface, it will be close to that. So and after that, it simply behaves as a point charge. This result is due to the point charge, right? So inside electric field is 0. That's why simply potential will be constant, and the value of the potential will be q upon 4 pi epsilon r, okay. So why is this this value? Just due to this surface charge, right? Due to this surface charge, okay. Now with the help of this concept, can you solve this particular question? So we have determine the potential at points M, N, O, P for the arrangement shown below, all of them are hollow spheres. Now with the help of this concept, can you find out the potential at M, N, O and P? Can you solve it for me? So what will be the potential at M? Okay, so potential is a scalar quantity, so I can simply add everything up. So again, this formula I can use, right? This formula I can always use. Sorry. So here, if I'm at M, right, potential due to all of the spheres will be simply constant. What will be the value? It will be simply charge divided by the radius. So here, if I observe inside a sphere, inside, this is inside, and this is outside. Inside the potential is constant, that is charge divided by the radius. So I will actually do that. So this I can write directly, K will be common, and everything K is common, charge divided by radius. So for the first sphere, Q by capital R, Q by capital R. For the second sphere, 2Q minus 2Q by 2R. For the third sphere, 3Q by 3R. Because this point is inside all the spheres. So overall this becomes KQ by R. Okay, because this 2 gets cancelled, this 3 gets cancelled, this gets cancelled, only KQ by R. Now what about the endpoint? What about the endpoint? So at point N, what will be the case? At point N, for the first sphere, I am at outside. So if I am outside, right, I will directly take the distance from this center of the sphere to here, that is Rn. I will choose this Rn for the first sphere only. For the other two sphere, I am actually inside. So for the other two spheres, the potential will be constant. For this first sphere, the potential will be a function of distance from the center of the first sphere, Rn. So again, K is constant outside. This time, what will happen? Q will be at the top numerator, but at the denominator, instead of the radius of the sphere, it will change to the distance from the center. So it will be Q by Rn. All this will be same, it will not change because I am still inside the other two spheres. So this will be still same. Okay, so what will this become? This will actually become KQ by small Rn. Okay, because this and this gets cancelled. Now what about the point O? Now all these are computed with respect to, remember, infinity, reference. Again, K will be common. So here if I observe at point O, right, the first sphere, for the first sphere I am outside. This point O is outside the first sphere. For the second sphere I am again outside. For the second sphere also I am outside I'm outside, right? So if I am outside, basically, so what will happen? So the potential due to first and second sphere will depend actually the distance from the center of the spheres. As they are concentric, the distance from the center of the spheres to this point will be same, that is RO. And for the third sphere, again it will be the dependent on the radius of the third sphere because it is inside the third sphere. So this will become Q by Rn plus minus 2Q by RO. Sorry, not Rn, sorry, it will be RO, right? Distance from the center is RO. Distance from the center is RO plus 3Q by 3R. This will remain same, this will not change. So what will happen here is this will become minus Q by RO, right? Minus Q by RO. So if I take this common, KQ, if I take KQ common, right? If I take KQ common, what will I be left with? This will be 1 by R minus 1 by RO, something negative, because RO is less than capital no, something positive, because RO is greater than capital R. Okay, so this will be the case. Now what about the point P? Okay, I am solving for all of them. Point P, now I can observe that this point P, right? Point P, if I observe, point P is actually outside everything. Point P is outside everything. So I just need this distance from the center of the spheres, that is RP. So everything will be same as the first one, just here instead of capital R, right, just it will be changed to RP, else everything else will be same. This, all of this will become RP. So this becomes plus Q by minus Q by RP. So this is 3Q by RP. So this becomes plus, so 4Q by RP, right? So yeah, this becomes, is it correct? Yeah, sorry, this is minus Q by RP, right? So this will be 2Q by RP. Okay, so that will be the answers. Pretty simple, right? Nothing changes here. Just for the next case, that is due to the solid non-conducting sphere, again everything will be same, right? Behaves as hollow sphere, as it is non-conducting. Sorry, this will not behave. The perfectly conducting sphere will behave as a hollow sphere, but here things will change because we have derived the expression for electric field, right, inside a non-conducting sphere. Okay, if it is not a perfect conductor, right, then it changes. So if it changes, right, then the potential will be this. Now I will also tell you how can you find out the potential. How can you find out the potential if you know the electric field expression, right? I will tell you that. Don't worry, I will tell you that. Okay, just in the next few slides I will explain how can you find out this expression from this expression. So just remember this. Just remember this, or you can derive this easily. We have derived this with the help of Gauss law. So just remember this. I will tell you just how to get to this value. I will tell you. Just remember this. Okay, I will tell you how to get to this. Okay, this expression looks bit like difficult at first, but I will explain how you can derive this. Okay, so this is the expression for potential due to a non-conducting sphere, because as this is a non-conducting sphere, charge can actually reside inside the surface. This is a solid non-conducting sphere, hence charge will reside and electric field will obviously be there, and potential will not be constant anymore. Potential will actually change. Okay, so for a solid sphere, radius r is uniformly charged. The electrostatic potential V is plotted as a function of distance r from the center of the sphere. Which of the following graphs best represents the resulting curve? Now, if they have mentioned, right, a solid sphere of radius r is uniformly charged, so you assume that if they are telling it, okay, it is uniformly charged, how can a solid conducting sphere be uniformly charged? Not possible, because electric field cannot exist inside the surface, inside the volume of the sphere. So I will assume they are telling me uniformly charged. I will assume they are talking about non-conducting sphere. Non-conducting sphere, because for a solid perfect conductor, this type of situation is actually impossible, not possible. Okay, so I will assume non-conducting sphere. Now, like right now I will derive the graph through this expression, but if you are thinking that how will I remember this expression, I told you, right, just remember this. I hope you know how to remember, and I will tell you how can you get to this expression. Don't worry, I will tell you that. Okay, so what I can tell is that here if I observe that V at center, right, what is the potential at the center of the sphere? That is when r is 0, right, this some point P is this basically r, right? This is the distance smaller. When this smaller is, when I am at the center, if I am at the center, this becomes K into 3 by 2 Q by R. Okay, and when I am at the surface, okay, when I am at the surface of the sphere, I will put R equals to capital R. So this is will become 1. So it will be 2, or it will be simply K by R, KQ by R. So at the surface, the potential is lower than the center. So center potential will be higher. Center potential will be higher. So at R equals to 0, potential will be higher than the potential at R equals to capital R. After that, it is only reducing, because as R increases, it is inversely proportional. So this is not possible. This is not possible. It is not constant. It is reducing. this may be possible, this may be possible. Now which one shall I choose? Okay, so obviously here it is telling me that the potential actually reduces linear, and here it is telling me that the potential actually reduces, but it reduces non-linearly. Okay, now which one is the possible case? Will it reduce linearly? Is there any linear function you are seeing in this thing, right? Nothing is linear, right? It is quadratic and dividing, so it is definitely non-linear. So it is not linear, so it is non-linear, so option C will be correct. Just through the graph you can say, or you can identify from, they will give you a few points as well, or you can identify from maximum minimum concept as well. Here you are seeing sharp change, right, from the slope changes sharply, which is not possible. Slope will not change sharply, actually slope will change continuously. Okay, so now I will explain how can you derive the electric potential expression from the electric field. Okay, so we will use a basic formula only. So I know what is the electric field inside, right? So how do I compute the electric field? Okay, inside a non-conducting sphere. For a conducting sphere it will be same as hollow sphere only, everything will be same. So what will I do? I know basic expression, right? It is minus E dot dl. So one point will be r equals to infinity. Okay, r equals to infinity to r equals to r. Why? Because at r equals to infinity the electric field will be 0, and hence the potential will also be 0. That this much information I know. So I will be able to calculate the potential at P. So Vp will be, what is dl? As this is in the spherical coordinate system, I am talking about inside the sphere, so I will use the spherical coordinate system only. So integration E is how much? kq not q, sorry, yeah, kq small r by r cube, and ar cap is there, air cap cancels each other out, and it is dr, right? So okay, something is, am I doing something wrong here? Okay, sorry, because like the expression for electric field actually changes. So what I will do is, I have to break this down, right? I have to break this down into two parts. So first part I will go from r to small r. Actually this part should have been like this. Plus infinity to am I doing this correctly? Yeah, this should go from infinity to r, then from r to small r. So from infinity to capital R, the expression for electric field is actually something else, right? What is the expression? The expression is this, right? If you remember, the expression is this, q by 4 pi epsilon r square. So it will be kq by r square dr. Okay, both are in air cap directions. So what will this become? This will become, if I just simply integrate it, it would be minus will still be there, and this will be minus kq by capital R, and okay, minus sign is outside, yeah, that is fine, that is anyway 0, plus what will this be? kq by r cube is outside, and this will be r square by 2. R square by 2 is here, r square will be here. Okay, I hope you are not confused with small r everywhere. I'm just doing the integration. So this will be, just hold on, this will come out to be Vp is equals to minus kq by r plus kq by r cube r square minus capital R square, correct? So what will this come out to be? So I can take the minus side inside, so kq by this kq can come outside, right? Minus sign can go inside, so this will be plus 1, and obviously 1 by r is here, plus and minus sign is inside, r square by r cube, and okay, and this becomes plus as well, 1 by r, correct? So this comes out to be kq 2 by r minus r square by r cube. Yeah, sorry, actually I missed the 2 here, right? This was a 2, like if you observe, this was actually 2, so I missed the 2. This should be 2, this should also be 2, and if this is 2, right, so this will become 3 by 2 actually. This will become 3 by 2r, and if I take 3 by 2r common, right, if I take, like here also this has, they have done the same thing only. Oh, okay, they have just taken 1 by 2r common. If I take 1 by 2r common, this will be kq by 2r. Okay, okay, just hold on. Yeah, this should also be 2, right? So this will be 3 minus r square by r square, capital R square, into this. So obviously your whole potential, right, potential actually comes out of this expression. So you can derive it. It will take you time, but with practice it will not take you time. And if you want to write it instantaneously, you have to remember there are trade-offs, right? You gain some, you lose some. So obviously now we'll start the next topic. So this is electric field as a gradient of electric potential. Now I know how to find electric potential if I know the electric field. Now if I know the electric potential, how can I find out the electric field? That we'll understand from now onwards. So we know one expression, right? Del V, that is change in potential, is equals to minus E dot dl, integration of E dot dl from A to B along this closed line. So from this, what can I say? I can say that dV is equals to small change in voltage, right? Small change in voltage. If I just move this much, let's say very small, right? Very small quantity. If I just move here in this dl direction, what will be the potential change? It will be dV, right? If I just move in this dl direction, the potential change will be dV. And what will be the dV equals to? That dV equals to will be minus E, because I will apply the force in the opposite direction, minus E dot dl. This I have derived at the starting of electric potential, right? So now this, like, just to give you a feel, I will tell you, this is not the actual proof. Okay, just to give you a feel, I will tell you. So what is E dot dl? E dot dl is minus E magnitude dl magnitude cos theta. Okay, the angle between the electric field and the potential. So this is the angle. Now if theta is 90, then this expression actually, like, I am simplifying things here, just bear with me. This expression becomes, on the left hand side I have dV, and if I just assume this as dl, dV upon dl, just bear with me here, okay? This is not the actual proof, so don't give me any abuses. So this will be dV upon dl equals to minus of E, if I am just talking about the magnitude of this, when this is what, theta is 90, okay? And dV dl is maximum. So this is maximum when dV dl is maximum when theta is 90. And when the derivative of something is maximum, what do I call it? What do I call it when the derivative of something is maximum? Remember, something maximum, right? Differentiation, it is increasing in that direction in maximum possible manner. That is gradient. Gradient tells me the direction about which I can increase in the maximum manner, right? So this in short actually means that mainly we're talking about this relation. This relation is very, very important. That electric field is actually gradient of electric potential. Electric field is gradient of electric potential. So I can say as dV upon dl maximum is equals to E, so I can say del dot V or not dot v, sorry, del v, because v is a scalar quantity. I cannot take the divergence or the curl, I can just take the gradient. So del v equals to minus e. This is a very, very important expression. This you should know in the vector format. Okay, in the vector format, because if I take the gradient, it actually gives me the vector, right? So that is what my elliptic potential is. Or I can write it like this in a better way. What I can do is I can actually swap the positions, because like I can write electric field is equals to del grad of potential, right? Electric potential. Okay, so now this is the thing that we'll use in the next few slides. So if the electric potential in a region is given like this, where x is in meters, what is the magnitude and direction of the electric field at x equals to 3? Can you solve it for me? Easy, right? You can solve it. You know the electric potential, you can easily solve. How to solve? This is in the Cartesian coordinate system. So we'll find the gradient in the Cartesian coordinate system. We know E vector is equals to minus gradient of electric potential. So it will be simply minus of gradient in Cartesian is very simple. This will be only in, this is only in the x direction. So we have to differentiate with respect to all the elements, with respect to all the variables. This is minus 7x, so this will come out to be minus 7, right? I hope you know how to find out the gradient. And obviously ax cap will be there, ay cap and az cap are 0, because del y and del z are 0. So E electric field is actually constant in the x direction of 7. Okay, so here this unit also you have to identify. This is in coulomb per what? Coulomb per not coulomb, sorry, Newton per charge, because if you remember, electric field was defined as what? It is force divided by test charge q naught, so Newton per coulomb. So here which of the following is correct? Minus 11 Newton per coulomb in positive x direction. No, positive x direction is correct. So positive x direction, these two will be correct, but negative x direction is incorrect. Okay, 11 in positive x direction, 7 in negative x direction, 7 in positive x direction. Yeah, 7 in positive x direction, that is correct. Magnitude is 7 and the direction of the electric field is in the positive plus ax cap, right? So this will be the answer to this question. Now you can solve this question as well, right? This is again simple question. You just have to find out the gradient of this. So yeah, this is a question of a book, very famous book. So can you compute the gradient of this? You have to find out the electric flux density. To find out the electric flux density, what do you know? Electric flux density is equals to sigma upon electric field intensity. So if I find out electric field intensity, I will be able to find out electric flux density. Okay, so first of all, I will compute electric field intensity. It will be minus del v. Now this is in the spherical coordinate system, so I will solve it using the spherical coordinate system. So how do you find out the gradient of this thing? So first of all, you have to recall what was the gradient. Gradient was this, right? You have to write the length dl vector first. It is like, if you tend to forget this, right, write in your short notes, and this is how you will recall. Basically it will be dr in the spherical coordinate system, that is ar cap plus r d theta a theta cap plus r sin theta d phi a phi cap. Okay, so this is what? This is basically this is now from here I can recall my h1 is 1, my h2 is r, my h3 is r sin theta, right? h3 is r sin theta. Now I remember, right, what is the gradient of a particular function? It is simply in any coordinate system, it is 1 by h1 del. For divergence, actually the internal multiplication happens, but here no internal multiplication happens, so things will be pretty simple, right? So this will, like, for spherical I will write directly for spherical. Right here it is 1 by h1, that is 1 by 1 del r del v del r a r cap plus 1 by h2, that is r del v del theta A theta cap plus 1 by r sine theta del b del phi a phi cap. Okay, so this will be the expression for gradient, so I can simply solve it, right? So my electric field in vector format is minus of gradient of this, so basically minus of gradient of del r should be like this, 10 by r square sine theta cos phi. Okay, a r cap plus del of del r, like as it is a function, not del r, sorry, the del theta, and obviously I have 1 by r as well, right? 1 by r as well. Same thing will be copied here as well. Okay, this will be theta plus the same thing will be copied here as well. Just here, instead of it being 1 by r, this will be like, let me write this better, 1 by r sine theta, this will be phi, this will be also phi. Okay, so if I overall compute this thing, what will I get? So this actually becomes minus, now here cube is coming, right? So minus 2 will come in front, minus 20, and everything else remains same. Okay, this will become r cube actually. Okay, this will become just r cube. I can reduce the size actually of this whole thing to accommodate more space. And if I differentiate this with respect to theta, this will just become cos theta. Okay, everything will be same, and r is getting divided, so this will again be r cube. This will become okay. Now what about the third case? So third case, sine theta, this is with respect to phi, right? So this will become minus sine phi, and sine theta and r sine theta will get cancelled. So what will happen is, I can copy this actually, this whole thing is here, this will get deleted, sine theta will get cancelled, this will become sine minus of sine of phi. Okay, and this will actually become r cube. Okay, so overall the expression will get condensed, and I will put the values of basically phi. Okay, electric field at point P. What is the point P? P is equals to what? P is 2 comma pi by 2 comma 0, 2 comma pi by 2 comma 0, so 0 degrees. So this will become 0, so pi by 2 is 90, so this will become minus minus is at the outside, minus 20 by, and this is 2, right? So this will be 8. Okay, and AR cap. Now if this is 90, right, so this expression goes away, this is 0, and here if this is 0 degree, this expression also goes away, so only I am left with on the AR cap direction. Okay, so this will become 20 by 8, or I can say 5 by 2, or I can say 2.5 AR cap Newton per coulomb. Okay, so what will be my flux density? Flux density will just be 2.5. Have they given me epsilon? They have not, right? They have not given me epsilon, so I will just write in normal expression that 2.5 epsilon AR cap, this will become coulomb per meter square, because epsilon has a unit, and what is the unit of electric flux density? Flux density, so charge per unit area. Okay, so this will be the answer. And for the second part, right, this was the A part, This is a question from a very good standard book. For the second part, I'm giving you homework. Try to do, because it is just computation of work done. Calculate the work done in moving the charged particle from point A to point B. Okay, so you have found out the expression for electric field, right? So now you have to find out the work done. So you can, I hope you can find out just Q minus Q times integration from A to B E dot dl. Okay, that much you need to do. This will be lengthy. Try it, and I will solve it in the next lecture. Okay, so like let's understand few significance of this okay, of this electric field as a gradient of electric potential. So del V will be what? Del V will be a normal vector to V equal to 0 curve in the direction V greater than 0. Okay, where V is increasing. So minus del V will be what? Just opposite. Normal vector to V equal to 0 curve. Normal vector to V equal to 0, because I know what does gradient signify, right? We already know that thing. So minus to del V will be normal vector to V equal to 0 curve in the direction V less than 0, where V is decreasing. So basically where potential decreases. So these two things you have to keep in mind. Electric field is a normal vector to V equal to 0 curve, where the basically V equal to 0 means there is no change in potential. Okay, 0 potential difference. Potential, if you remember, it is always with respect to 2 points. 0 potential difference in the direction in which V reduces. Okay, where V reduces. So from here the concept of equipotential surfaces come. Okay, an equipotential surface is a surface in which the electric potential V is constant at every point. Look, the potential will not be 0, but it will be constant. So potential difference will be 0. The electric field is always perpendicular to the equipotential surfaces, because potential difference between any 2 points on an equipotential surface is 0. Now, if the potential difference is 0, that means what? That if I move a particle, right? Let's say, okay, I have been again in back. If I move a particle here, let's say this point is A. Okay, this point is A and this point is B. If I just move a particle from A to B, what will be the work done actually? So let's say I have a point charge Q. Okay, this point charge Q actually produces an electric field like this, correct? Now, if I am at this point, what is the electric potential here? The electric potential is KQ by RA, correct? And what is the electric potential here? The electric potential is KQ by RB. And what relation do I know about RA and RB? RA is equals to RB. That means VA is equals to VB. That means what? That means basically the potential difference is 0. That is VAB will be 0 as their same potential. That means like electric field won't be 0. But what I can say that this is a equipotential surface, as electric field will be perpendicular to this. Because if I observe one thing, what do I observe? Let's take another point C. So can I say this is, what is the distance? This distance is RC. Now what can I comment about the electric potential of C with respect to A and B? I can say that VC will be less than VB or A. Okay, why is that the case? Because RC is greater than RB, and the electric potential expression is KQ by R. So what is happening? Try to visualize this thing, right? This statement. Try to visualize this statement. Here, as I am moving along the surface, along the direction of the electric field, potential is reducing, and it is perpendicular to the surface, Gaussian surface, right? This surface, this total spear-like surface is equipotential surface. This surface is equipotential surface. Okay, but these two surfaces are not equipotential. The potential is different, right? At C point, the potential is lower. But what I can say, electric field is going, it is perpendicular to these two surfaces, which of them individually are equipotential, and electric field, the direction of the electric field is in the direction in which electric potential is reducing. Okay, so I hope you are understanding the point whatever is written here. Electric field will be a normal vector to V equal to 0 curve. So it is V equal to 0. V equal to 0 is here. Potential is almost 0. Okay, and it is on the direction on which potential is reducing. Okay, I hope you understand that point. Okay, so therefore E must be perpendicular to the displacement of the surface. So as the surface is here, E is always perpendicular, right? Wherever I move, E will be always perpendicular to this, right? Always perpendicular to the sphere. Gaussian surfaces are often equipotential surfaces in the context of symmetrical charge distribution as spherical or cylindrical symmetry. So you can go back to your notes and just observe whatever surfaces, Gaussian surfaces we assume, right? Those were always equipotential. So Gauss law only helps when there is symmetry, and as they were equipotential, so finding the electric field expression was very, very simple. Obviously we can use the Gauss law for any arbitrary shape, but we will not take help of the symmetry and things will become very, very difficult. Okay, things will become very, very difficult to prove. So the main crux of this is that this thing is telling me as my distance, that is r, is increasing, my potential will reduce, and that will be the direction of electric field. Okay, that will be the direction of electric field. If my potential reduces, that will be the direction of electric field. I hope you understand this point. So yeah, that was about equipotential surfaces. So now we will do few questions, and then we'll wrap up this lecture. So can you solve this question? The points resembling equipotential surfaces are. So here are 4 points which are equipotential surface. This is actually electric field lines, right? Electric field lines. Now from here to here, if I move from here to here, move from Q to P, will there be some work done? Yes, there will be some work done, because like let's isolate the cases, right? Let's isolate the cases. Okay, I will just duplicate this one and take a new page. Okay, I will take 4 cases. Okay, or 2 cases should be enough actually. So if I am moving from here to here, this is my DL vector, and what about the force? Force also is in this direction, right? So theta is 0. So obviously my delta W is not equal to 0. My delta V is not equal to 0. So this can't be a equipotential surface because the potential is changing. What about from here to here? If I move from here to here or here to there, like from here to here or from here to here, what I can comment is that what is my force direction? Force direction is in this direction, right? External agent. So again, the angle theta 1, theta 2, I can comment that theta 1 and theta 2 are not equals to 90. This much I can say, right? Theta 1, theta 2 are not equals to 90, right? This much I can say. And if they are not equals to 90, I can surely say, as it is a function of cos theta, I can surely say that my del W will not be equal to 0. Hence, my del V will also not be equals to 0. Now, what else can I say about the third case? Third case is if I am moving from here to here. If I am moving from here to here, so what is my force? Force is here, right? So it is 90 degrees. So I can directly say my theta is actually 90 degrees. I will use some other color. Theta is 90 degrees. So if theta is 90 degrees, what can I say? I can say that my del W will be 0, as it is a function of, as my del W is proportional to the cos of theta. Okay, so hence my del V will be 0. If my del V is 0, that means potential is same, it is equipotential. Okay, equipotential surface, equipotential, right? So S and R both are equipotential surface, right? S and R both are equipotential surface, because if I'm going through this surface, right, if I'm creating like going through these 2 points, they are equipotential. Okay, not surface, equipotential path. I can say path or surface, whatever you want to say. Okay, so in this case, S and R will be correct option here. Okay, so one thing you have to note is that your what is the key point here about equipotential surface is that the path that you are taking the test charge should be always perpendicular to electric field. Then those points will be equipotential. If the electric field is always perpendicular along the path that I am taking, the test charge, if it is always perpendicular to electric field, then those points will be equipotential, right? Okay, this is a summary of this particular statement. So let's solve another question. At a point in space, the electric field point towards north. Okay, so north is at the top. Just have our geography in check. North, south, this is the east and this is the west, right? So north is at the top, and electric field, they are telling me electric field is actually pointing at the top. Okay, in the region surrounding this point, the electric potential will remain constant along which direction? Okay, along which direction? Along the north direction. Will the electric potential be constant along north direction? No, right? Because dl and E vector are both parallel. South direction, again dl and E vector are both anti-parallel. No. North south direction, north to south. North south means this, right? North south. Okay, this only. No, right? East west. Okay, east to west. Here in this case, right? In this case, what I can say, that my dl and E vector are always perpendicular. Okay, dl and E vector are always perpendicular, so option D will be correct. So whenever the dl vector and E vector are perpendicular, it is called as a equipotential point. Like those points are equipotential as the electric potential remains constant throughout that direction. Okay, so basically that's it for this lecture. I hope you enjoyed this lecture. I tried to explain everything crisply and clearly. So we will start the next lecture, that is lecture 4C. That will be also related to electric potential and few new concepts, that is electric dipole. Also we'll solve this homework question that I gave you as homework. Okay, thank you for watching and happy learning.